Hello everyone and welcome back. So in this video, I'd like to introduce you to a couple of important groups which we will soon encounter sooner or later in this course or in some other courses. So our topic for this video is examples of groups. So for now, I'd like to introduce you to a couple of very simple but recurring groups, and progressively we'll go on to explore some of the more complicated groups. So our first example, the simplest abelian group called C2, which contains only two members. One is A, is just a generic member, and the other is identity, written as E. So the relationship between these two elements are quite expected, which is A star A, which we can write shortly as A squared. And if we write that, it just means that this is analogous to the multiplication operation. And this should give us E, which is the identity. Notice that A is its own inverse. So A inverse should mean A, because we know when one of the members of the group is multiplied with another member, and if the product gives us the identity, then the latter member must have been the inverse of the former one. This group can physically signify a lot of things. One of the things that it can denote is a rotation through the angle pi. So that's our first and probably the simplest example. One of the definitions that we can now provide is something called the order of a group. And by order of a group, we mean the number of elements in a finite group, because for an infinite group, the order of the group is simply infinity. So that's just a trivial piece of information, but it's actually significant when we deal with finite groups. In this case, the order of C2 is simply 2. Another group, which is our next example, which is also a very simple group, is the group Zn, which is the group of integers modulo n. So that means you take an integer, you take the modulo n, and all the integers modulo n forms a group. So for example, Z2, it contains the group elements 0 and 1, and this is a group. But under which operation? And the operation is under addition mod n. That means you add two numbers, you take the modulo n or mod n, and you form a group. The Zn forms a group under addition mod n. Notice that Zn is an abelian group, and most importantly, we notice the similarity between the previous example and Z2. To be precise, we can form a 1-to-1 correspondence between Z2 and C2. And this thing, which we'll now name something and then later explain it, this thing is called the homomorphic relation. And this is written as Z2 this symbol C2, and this is the symbol of homomorphism. Homomorphism. We can also define the following group, which is Zn, but this time n is a superscript, whereas in the previous example we wrote n as a subscript. And this is the group of the nth roots of identity, or just simply the nth roots of 1, and together they produce a group. It is also an abelian group, and the order of this group is n. So for example, Z2 consists of only 2 members. One is 1, which is the identity in this group, and another is -1. And notice that previously when we explained C2 group, we said that one of the members is A and another is E, and the only relationship that makes sense between them is A squared equals E. And in this case we can associate A with -1 and E with 1, and notice -1 whole squared will give us the identity 1. And so it is clear that Zn contains a group under multiplication, yet there's something very, very mysteriously resembling between the Z subscript n group and Z superscript n group. Notice they're both abelian, they're both of order n, although the binary operations and the group members are totally different. So Z subscript n and Z superscript n, these two are mutually homomorphic. To further exemplify, Z3 would be the group consisting of 1 and then e to the power twice pi I divided by 3 and e to the power 4 pi I divided by 3. And in general, Z to the n would comprise of the element e to the power twice pi j divided by n, and there has to be the complex unit I multiplied with it, where j is simply 0, 1 up to n minus 1. So this is the group of the nth roots of identity under the operation of multiplication. Let us now talk about a more complicated group, which we denote by Sn and is called the permutation group. So this is a permutation group, and this group is an ordered set of n objects. So if we write 1, 2, 3 up to n, then all the permutations of this set will be the members of this group. And this group is non-abelian in general. It is non-abelian. So generally, 2 of its elements do not commute with each other. And also, the order of this group is n factorial, because there are n factorial ways to rearrange n numbers. The set of positive rational numbers form a group under multiplication, and evidently this group is an abelian group. For the first time, we've got a group whose order is infinity, because there are infinite of them. The set of real numbers R forms a group under addition. Notice it is also an abelian group, and it is a group of order infinity. Plus, this group has identity element 0, that the identity is 0, and for any real number u, the inverse is of course negative u. Our next example includes complex numbers. So all complex numbers of magnitude 1 can be written as e to the power I phi, where the parameter phi can take continuous values from 0 to twice pi. And this group is called the U1 group. They form a group under the operation of multiplication. So we have e I phi 1 times e to the I phi 2 equal to e to the power I phi 1 plus phi 2. This is also an abelian group and of order infinity, and the identity element, the identity is simply 1. This group can also be thought of as a generalization to the group Zn, with n going to the limiting value of infinity. And so this group will give us U1. And the reason there is a 1 is because it has one continuous parameter. Notice that this statement here may cause a bit of confusion. For an element e to the twice pi I j divided by n, if n goes to infinity, then of course in order to keep the exponent finite and equal to phi, we must ensure that as n goes to infinity, j must also go to infinity. So this is a bit of detail that absence of which might have caused some sort of confusion. I just wanted to clarify it. Under this limit, this element of Zn corresponds to an element of U1. The example of two-dimensional rotation in the Euclidean plane forms a group SO2. 2 denotes the 2 dimension, although this group has only one continuous parameter, which is the rotation angle phi, and they compose as r of phi 1 times r of phi 2. This is equal to r of phi 1 plus phi 2, and this is also an abelian group. That means this is equal to r of phi 2 multiplied with r of phi 1, where r of phi has the generic form cosine phi sine phi negative sine phi and then cosine phi. Three-dimensional rotation, they however do not commute with each other, but they create a group called SO3, where 3 again signifies the number of dimensions. Since the members of this group do not commute, this is an example of a non-abelian group. As a final example, I'd like to mention the boosts. Boosts in special relativity also form a group, so they connect the transformed coordinates to the coordinates before transformation, and they have this generic form of cos hyperbolic phi sine hyperbolic phi and then sine hyperbolic phi cos hyperbolic phi. And for two successive boosts, the boost angles, which are the angles of hypertrigonometric functions, add to each other. So there we have it, 10 examples, very interesting examples of groups. There are hundreds and thousands of examples, but there are only a few examples which we'll need in order to understand the particle physics better. Thank you very much.